Our next speaker is Aaron Zimmerman from here at UT. He's a gravitational wave physicist, and he will tell us about more surprises hoped for, if not yet found.
Don't promise too much from me, Jacques. Well, thank you, everyone. It's a real honor to be here, and it's really wonderful to see so many people here. And it's really difficult to follow the previous talk. But I'd like to make sure that everyone here is excited about gravity and cares about gravity. So that's going to be what I'll try to do today. So I'll be telling you about gravitational waves and, time permitting, one way at least that we can try to use them in the future to search for unexpected discoveries. So people have been giving their remembrances for Steve, and I thought I should say something as well. As someone that was trained in that more geometric side of relativity, Steve's work did not directly influence my research life, but I knew of him from my particle physics friends as a legend and a giant. And so once I had come here and interviewed and was heading home, Steve reached out to me, and this was, I think, really my first interaction with him. He wrote a really kind email, first of all, emphasizing that he was interested in gravitational wave observations, which was really wonderful to hear, and that at least he would be interested in hearing about my work if I were to come to UT. But I think the thing that really touched me was this last sentence in closing the email, which is what is probably more relevant to you, is that you will like it here. Austin is a strangely lovely place to live. And it was that poetic turn of phrase, strangely lovely, that I think really told me more about Steve than about Austin. But it really, I think, touched on something very personal. So I'm sad that I didn't get very much time with Steve. I am very grateful that I got at least to talk to him a little bit. So today I'm going to be presenting at the top of the talk some results which are from a large number of people. I'm a member of the LIGO Scientific Collaboration. I work on measuring the properties of the binaries we detect in gravitational waves. This is not a talk on behalf of the LIGO, Virgo, or Kagra collaborations. It's a talk on behalf of myself. What that means, of course, is that credit goes to everyone, and any mistakes, missteps, misstatements, you can blame those on me. Now, Saul opened his talk by mentioning that we're undergoing a revolution in the field of gravitation, both experimentally and theoretically, because the observations by these incredible detectors that Gabby described are driving new theoretical advances. So I won't spend any time talking about those detectors because those have already been covered in Gabby's great talk, but instead I'll just remind you of some things that have already been said. The way that the current network of ground-based gravitational wave detectors works is that we carry out a sequence of observational runs, followed by breaks in which the detectors are improved and commissioned. And we are now in the middle of our fourth observing run. During this run, we have already announced 160 low latency candidate detections for gravitational waves. I got to add one this morning as one rolled in. And here, this is the events that we have actually published on. That what you can see here is on the x-axis is this measurement of effectively our sensitive distance to binary neutron stars. That's just one metric for our sensitivity. And we get the expected linear scaling in volume with the cumulative number of detections. But the thing that's always been really striking to me is this is the first observing run, second, third. And while they are slightly different in duration, the detections basically went a couple, 10, 100. And that's because we are sensitive to the amplitude of these waves. So the amplitude falls 1 over distance. If we double our sensitivity, we actually pick up 8 times as many signals. So the volume of detections we make just goes up and up over time. And that really is transforming the field every single day. I'm going to start this talk with just a few highlights from 03. And I'm going to show you the same plot that Alessandra had in her talk. We have all of the detections made through the third observing run, plus the only thing we've published on from the fourth observing run so far, depicted in this plot, along with a few other things. So the vertical axis is the mass of each of the individual compact objects, which then merge into a final compact object. The x-axis is artistic. Here, we also have depicted all of those neutron stars and black holes that were previously detected, or not just previously, but detected in electromagnetic observations. And what's striking is that, at least in the electromagnetic observations, there's a big dearth of black holes in between sort of the upper threshold of neutron star masses and about 5 solar masses. And this is known as the lower mass gap. Now, this could be because there's a real physical mechanism that prevents black holes from forming around these. There's some threshold mass for black hole formation in the collapse of stars, or it could be an observational selection effect of some kind. We, of course, have a completely different set of selection effects, and we are quite capable of detecting things in this gap. Another thing I want to point to, just so you see, is that the typical system we're seeing is a binary of black holes with masses around 20 to 30 solar masses. This what you see here, this overdensity, I really want to emphasize, this is a selection effect, okay? It is not that most of the merging systems are at these masses. In fact, most of the merging systems are at these lower masses, but we strongly select for more massive systems. And so we have to incorporate that when we analyze for the population that underlies our detections. So I'm going to focus on some of the highlights from the third observing run, as I mentioned. And so the first one I'll mention is one of the first exciting detections in the third observing run. At this point was several years ago, I'm afraid, was GW 190425. This was the second detection of a binary neutron star. And I think the thing I like to highlight for this system is something that tends to go under the radar in the external community. This was detected with a single detector. So often we talk about how we use multiple detectors in order to get a coincident detection. But in fact, we're at a place now where we routinely make detection statements when only a single detector was on, and therefore only a single detector was observing. So here, plotted on this plot, is the signal-to-noise ratio of our matched filtering. That is the typical strength of signal measure. But we also use a variety of signal consistency tests to try to rule out instrumental artifacts. On this plot, the lower you are, the better the consistency with theory. And you can see this is the background of noise in the detectors. And this is this detection of a binary neutron star well off of the background, which is what allows us to make this detection statement. Unfortunately, because there was only one detector active plus Virgo at a lower sensitivity, this sky map is that banana tree that Sinyu mentioned. This could not be localized. And so there were no electromagnetic observations that were made of this particular system. What was cool about it is that it is a more massive binary neutron star. While each individual neutron star didn't have a mass that was an outlier, the system as a whole has a total mass well above 3 solar masses, which makes it a total outlier from all of the galactic binary neutron stars we know. Maybe there's a bunch of galactic binary neutron stars we've been missing due to a selection effect. Maybe there's a new kind of system out there. That's still unknown. The next weird system was this mystery system that Alessandra talked about a bit, so I'll skip over it very quickly. But it's a system that had an extremely high mass ratio, and because of all of the sophisticated modeling advances that theorists have been able to make over the years, we're able to constrain the masses of the system very tightly. And we find that the secondary is in this odd place where it's more massive than we think a neutron star can stably support itself against its self-gravity for a long period of time. But it's also way, way, way less massive than any other of the observed black holes that have been seen up to that point. And so we really don't know if this secondary was a neutron star, a black hole, or something more exotic. And only time will tell if we detect more such systems so that we can learn more about these kinds of things. Another oddball and unexpected one was our most massive binary black hole detection at the time. So this is depicting the strain as a function of time in the 3 detectors. It was detected in all 3 detectors. And what's striking about this is really you only get about 1 cycle of the orbit before the 2 black holes merge together and perform this ring down phase that Saul described on the first day. And so this signal is mostly merger and ring down, which gives it this sort of blobby spectrogram and actually makes it quite hard to understand its properties. Nevertheless, even though there's some systematic error, depending on how you model the system, it's very clear that it was a very heavyweight system, with the primary black hole being around 80 solar masses, the secondary around 60, and the whole system having a mass well above 100. We also think, although this is a little hard to be 100% sure of, that these black holes had very large spins and signs that the spins were tilted in the orbital plane, causing strong precession effects. Okay? If you want, you can ask in questions why this was such an interesting event. It's a little bit hard with traditional astrophysics to explain how we would get black holes of these high masses. It can be done with conventional effects, but people have explored a lot of interesting ideas, including, for example, Katie and her student Josh Ziegler, which proposed that dark matter annihilation heating mechanisms could help produce black holes of such high masses. The other really new thing that just started showing up in the third observing run that we hadn't seen before was kind of the last stamp we could add to our collection. We'd seen binary black holes. We'd seen binary neutron stars. We had not yet seen a neutron star and black hole pairing. But in the second half of the run, 10 days apart, we made 2 detections of neutron star black hole binaries. You can see here the mass distributions we infer from them. One of the 2 had a somewhat heavyweight neutron star and a somewhat heavyweight black hole. The black hole is so big that you tend to expect that it won't rip apart that neutron star, leaving matter outside to produce those spectacular electromagnetic signatures that Brian talked about in his talk, those kilonovas or gamma ray bursts. The second one was a little bit more promising in terms of that, but still not necessarily expected to produce a lot of electromagnetic radiation. And for the first one, we had, again, a very poor localization. It was really only detected in 1, maybe 1.5 detectors. And the second one also did not have a detected electromagnetic counterpart, unfortunately. So we're still waiting for the first electromagnetic counterpart to one of these neutron star black hole mergers. This dovetails really nicely into the first result we announced from the 4th observing run. And this is GW230529. This was actually detected sort of like the very first gravitational wave detection, detected a few days before we were actually going to officially start the fourth observing run. And so that was quite exciting. What this is it's this one right here in sort of the dark teal green. This plot is depicting all of the sort of neutron star binary, this neutron star black hole binaries or binary neutron stars that we've detected, so you can kind of see the range of systems we've seen. What this system was it was another neutron star black hole, but the black hole was very light. Okay, the black hole was probably between 3 and 5 solar masses, which puts it firmly in that electromagnetic mass gap. So we heralded this as our first firm mass gap detection. And so this tells us that, in fact, these systems do exist. And that's very interesting. Unfortunately, once again, this was detected only by 1 detector. So we did not localize it. So again, there was no real opportunity for astronomers to locate it in the sky. But there was a bright side to this dark event, which is that the fact that it even exists raises our prior hopes that we will detect electromagnetic waves from neutron stars. Up till this event, all of them had been sort of heavier black holes that would swallow their neutron stars whole. This one is not that kind of event. And so what this plot is depicting is the probability that any given neutron star black hole system is what we call EM bright, meaning that there's some remnant material outside of the black hole after merger. The gray line is what we had previously thought based on our observations from 03. The red line is, an order of magnitude higher, which means that we have more hope that we'll detect more of these systems that astronomers could follow up successfully. So those are the individual events, and it's fun to talk about the individual events, and any one new detection can really tell us entirely new things. But we're getting up to 100 events, and we're going to have 1,000 events before we know it, and then 100,000 events. What do we do with a large number of events? Well, obviously, we want to understand the population distribution of these things. And so one thing we do is we measure the mass spectrum of the black holes. And this goes back to what I was saying on the stellar graveyard plot. The mass spectrum is consistent with a falling power law with an extra bump, because we do have an overpopulation of those 30 solar mass-ish systems. And so this is a good fit to that system. But once again, the bulk of them are actually at low masses. We just are not so sensitive to detecting those. Again, not because we can't detect them, just because the loudness of the signal scales with mass. And so we have a larger volume sensitivity to the loudest signals. We can see them from far away, so we can see a large volume containing them. We've updated our rate calculations. I don't think these numbers mean anything except to the astronomy aficionados who themselves try to predict from binary evolution these self-same numbers. But one thing that came out of 03 was the first evidence that the rate of mergers is evolving with cosmic history, okay? And in fact, so far, that rate evolution posterior tracks perfectly with the star formation history. So this is an indication that at least at this level, the mergers are tracking star formation, which might be an indication that, say, the mergers happen promptly after stars are formed. If it takes a long time for systems to merge, you'll eventually see these decouple from each other and that will tell us more about where these binary black holes are coming from. I forgot that I have helpful words. There's also a dearth. We do have a confirmation that there is a dearth at very high masses. This is probably due to those same stellar processes that made that really massive event I mentioned a bit of a surprise. We're also very interested in measuring the spins of these binary black holes. It's amazing to me that we can do this, okay? Imprinted on the gravitational wave signal is the spins of the black holes, both their overall magnitude, but also their orientation relative to the orbital plane. What we found overall is that these systems are clearly spinning as a population. The population tends to peak around a dimensionless spin of 0.2, so 0.2 times the maximum that a black hole could ever have. But the thing that really tells us a lot of information is the spin orientation, okay? If the binaries are all sort of born together, the two black holes form from a stellar binary that was born and evolved its life together, you would expect the spin tilts to be correlated with the angular momentum, and you'd expect to have most of the systems lying over here with their spins more or less aligned. But if they're being dynamically formed in a dense globular cluster or nuclear star cluster, then the spin should be totally random. What we see is that it's somewhere in between. We actually have evidence that some of the spins are tilted even below the orbital plane. So there is evidence that there's at least one dynamical formation channel, but there's also not perfect isotropy here. So we have evidence then that there's multiple channels active in forming these binary black holes. It's not just astronomy we want to do with these systems and with this large data set. Sunil already talked about the cosmology we can do with gravitational waves. Alessandra discussed how by parameterizing our really sophisticated models of gravitational waves, we can search for deviations in those models and try to constrain deviations from relativity, including, for example, the dipolar radiation that she mentioned during her talk. One thing I'll mention is that we can use neutron stars to measure the properties of matter at the densest phases, far denser, at least for cold matter, than we can achieve here on Earth. The way this is done is that when the two neutron stars are close to each other, their tidal forces create a deformation. And the size of this deformation, lambda, encodes in one number the whole integrated structure of the neutron star. We actually measured this tidal deformation effect in the first binary neutron star merger. That's one thing that confirms for us, not just from the electromagnetic waves, but just from gravitational waves, that one of these two objects was a neutron star. Unfortunately, the second binary neutron star had a measurement of this tidal parameter that was actually quite broad and didn't really inform us over and above that first detection. But you can take this information, lump it together what we do know of nuclear physics, and we can begin to actually fill out this plot of the equation of state of nuclear matter beyond nuclear density, the P versus rho. And this is something we're going to continue to refine as the years go on. What's my time? 7 minutes. OK, I'll have to be briefer, unfortunately. I wanted to finish the talk by zooming in a little bit on a project in my own group, which is one particular way that we're trying to use gravitational waves to search for the unexpected. In particular, we're going to focus on the ring-down phase and try to understand how ring-down might proceed in a theory beyond general relativity. So the ring-down phase is this final set of damped exponentials that Saul discussed in his talk. And the thing that's attractive to me about the ring-down is that the modeling is somewhat simple, which I think gives us our best hope to take a theory beyond general relativity and actually make precise predictions for what we might expect during the ring-down from that theory, and then bring those predictions in line with observations. So the theory itself, at first glance, looks pretty hard. In order to understand ring-down, we have to be able to understand how waves propagate around spinning black holes. If we take the metric of space-time and split it into the Kerr black hole and some gravitational waves, this creates a set of partial differential equations which, while linear, are coupled, non-separable, and you basically have to do a simulation to solve them. But really amazingly, as Saul showed in his graduate work, if you focus instead on a piece of the curvature tensor, this is a complex curvature scalar that encodes both polarizations of gravitational waves in its two pieces. This obeys a wave equation which is decoupled from all the other pieces of the curvature, and remarkably separates with separation of variables, so you can solve it as an ODE system. When you then frame the right boundary conditions for ring down, this ODE system turns into an eigenvalue problem, and you can solve for the spectrum. And so we can do this very precisely. And then if you ever need to answer any questions about the actual structure of space-time, it turns out you can also use these curvature scalars to reconstruct all the things you need to know about the metric. The result then is that we know very precisely the spectrum of ring down. Basically, the spectra is completely determined by the mass and spin of the black hole. That's the O'Hare theorem. The mass itself sets the overall frequency scale of ring down. For solar mass black holes, it's about 16 kilohertz, well beyond our sensitivity in LIGO. But for 100 solar mass black holes, this puts us right in our most sensitive band. You can see that there's multiple angular harmonics with increasing frequencies. There's also those higher overtones that Saul mentioned, which are not depicted on this plot. And the other takeaway, which is kind of depressing, is that if you look at the quality factor of these oscillators, they're kind of crummy, quality factors of 2 to 3. They only execute a couple of cycles before they damp away. This is the fundamental challenge in doing spectroscopy with black holes. You just don't get many cycles to observe. But if you can measure even one ring down mode of the spectrum, you use its damping rate and its frequency to measure the mass and spin of the black hole. And with 2 modes, you get a consistency test. One of the exciting developments in this field, based on work both from Saul's group and further follow-up work by others, is that it's beginning to look like we actually can measure multiple of these ring-down frequency spectrums in current observations. There's still some controversy about this, but if you take a multiple overtone ring-down signal or a multiple harmonic ring-down signal, and you apply them to some of our best detections, so the very first detection, 150914, or that heavy-duty one that I told you was all ring-down, 190521, there's actually evidence that you can detect multiple of these modes in these events. And that gives us hope that we can use these events to test relativity. And so this was done by the LIGO-Virgo-Kagra collaborations. There's a couple different ways that this is approached. In one, you use the fundamental quasi-neural mode plus its first overtone, and you combine those constraints on a deviation from one of those 2 modes across all the known events, and you get about a 25 to 50% constraint, dimensionless on that frequency. Another thing you can do is you can take all the information you gleaned during the in-spiral and merger, but allow the frequency of the quasi-neural mode, the fundamental only, to vary and constrain to see whether those deviations are close to 0. What I'm particularly interested in is finding specific theories and figuring out in a specific theory, what should these deviations be? The reason for that is, 1, it helps us to interpret these parameterized tests, but 2, it also actually allows us to create the most precise ways of combining many events together to get the strongest constraints we possibly can frame on these theories beyond GR, just using the ring down. So Kim put Lagrangian on her slide because she is a bona fide trained particle physicist. I put a Lagrangian on my side because I have bona fide envy of particle physicists. So what I worked on with my student, Asad Hussain, who, by the way, is a fantastic student trained both in theoretical methods and data analysis, and he's on the postdoc market, and you should hire him, is we considered a class of theories where we have the typical Einstein-Hilbert action, and then we have some unknown beyond standard model fields, which couple in a non-minimal way through some interaction term with the metric. And it's controlled by this epsilon parameter, which is some potentially dimensionless coupling, which we'd like to use all of our observations to constrain. Okay? This is a hard problem. First of all, these extra fields and the interaction create new source terms on the right-hand side of Einstein's equations. And you also have to figure out what the evolution of those new fields would be. The equilibrium solution will have this generic character that the fields themselves will be sourced by the background curvature, so that we'll have some small sourcing of the new fields by the curvature of the black hole. But then that sourcing of the new fields plus the changes to the Einstein's equations through the interaction potential will also perturb the metric at a higher order and cause a deformation to the black hole spacetime. And so you already have to understand what the background solutions are for the fields and for the metric just to get going. But then our dream is to perturb that, to allow both the fields to oscillate and to allow the metric to oscillate. And solving these together is kind of a horrific, again, large set of partial differential equations. But what we showed is that we can use the same sort of projection tricks to boil this down to a modified so-called Tucholsky equation. And this was done in parallel with another group who arrived at the similar equations at basically the same time. But what we did was we wrote down this equation, but we also have an idea for how to solve it. I'm down to 1 minute, so I'll just skip very rapidly and just mention that the trick comes straight out of junior level quantum mechanics. If we have a perturbed Hamiltonian equation, a perturbed eigenvalue equation, one of the big challenges is understanding how the actual solutions, the states, are shifted by the perturbation to the Hamiltonian. But we know that if I have a Hamiltonian that can act on the left, I can sandwich with the with the 0th order states, eliminate most of the terms, and algebraically solve for the energy shifts without ever having to know how the states shift. We can take advantage of the same story, and by defining an appropriate product, we can sandwich the perturbations to the standard black hole wave equation in between 0th order solutions, which we know how to do, and therefore derive just the shifts to the spectrum. It's straight out of quantum mechanics. This is some work that we developed in graduate school and that we're continuing to evolve and hopefully apply in the future. Now, we did this targeting charged black holes, which are a nice just sort of toy problem because they have the electric and magnetic fields as well as the metric, both of which get perturbed at the same time. But I'm going to have to skip all of this really interesting stuff we discovered along the way and just summarize. The third observational campaign by LIGO, Virgo, and Kagra has yielded many discoveries, but also these puzzling systems that we really need more observations to untangle. We've already finished the first half of the fourth observing run. We made 81 we've announced 81 candidates. Some of them are potentially neutron star black holes. The fourth observing run is still ongoing. And in the coming years, as Gabby mentioned, we're going to continue to upgrade the detectors so that they exceed their design sensitivity, add detectors to the network, and also eventually build the third generation of detectors, which will take us from, again, 10, 100, 1,000 to 100,000 detections per year, allowing us to actually detect all binary black holes in the entire observable universe. And that will hopefully be done in, what, 10, 20 years? So it'll be very exciting to see that complete transformation of the field. So I'll thank you for your time.
Okay, we have time for a few questions.
Hi, so I had some questions about the mass gap.
Yeah.
Am I correct in that this is an observational conclusion, not a theoretical one, or is it a theoretical
Yeah,
mass gap?
it's primarily an observationally derived thing. That's just because the physics of supernova is very complicated and has still been evolving even to today. And so it's perfectly reasonable to think that there might be some thresholding behavior that below some iron core mass, you'll produce a neutron star, and above it, you'll produce a larger black hole without there being a continuum here. And some studies have been done to try to understand that. But that theory there is very uncertain, and so this is all observationally driven.
Yeah, I was also, so you said that we were able to conclude that 230529 was a neutron star black hole merger, but not 190814. And if they're both in the mass gap, I'm a bit confused as why you have that difference in conclusion.
That is a great question. So it comes down to the fact, and I don't know if in my backup slides I have a nice plot. Let me unfortunately just try to squint with all of you at this plot I do have of the mass of this system, which is here. The subtlety comes down to this. This is 1908-14. Notice that the secondary is very well measured and above that region where we think neutron stars can stably exist. So it's most likely that this is a black hole, okay? But it's very light for a black hole. Meanwhile, this is the new neutron star mass gap system that I mentioned, it's clear that one of them is down below in the neutron star. It's clear that the secondary is almost certainly a neutron star, unless the upper limit for what neutron stars can be supported is very low, and this is very high in the statistical tail. Meanwhile, the primary is here, where it's certainly well above 3. A great question.
One more question.
You mentioned, so you mentioned the nuclear equations of the state of a neutron star.
Yeah.
You know, Steve was very much interested in the superconductivity, as you know. So for the neutron star, people propose the color superconductivity.
Mhm.
So I was wondering whether the gravitational wave detection can help you understand the equational state in the neutron star.
Yeah, so that's our hope. So I
And
think,
then also in which aspect you can learn the equational state.
right. So unfortunately, we measure from gravitational waves directly one number which is integrated over the entire density profile of the neutron star in some sense. So there are going to be many different kinds of equations of state which could be self-consistent with a given measurement. So this is going to be a place where theory and modeling modeling and observations really have to come together to give us a better understanding. One thing that could be possible is that if there were some neutron stars where there was a very dramatic phase change, so that the radius or distribution of mass inside the neutron star really was different from one mass to another, that's something we could show up by having two sort of dramatically different measurements for these tidal deformations in different systems according to mass. But I think it will be challenging to get direct information about the nuclear physics from there.
Okay. In light of the time, let's thank Aaron again.